Hello, everyone. I'm Billy Younger, and I'm going to try to start you learning special relativity. In this lecture, or in this little video, I'm going to first introduce the two principles of relativity, and then I'm going to use it to solve for the time dilation equation and actually use the actual principle, apply it to a certain situation, derive the time interval, and find out how the time interval is related to another time interval. I should start by saying that the special theory of relativity was published in 1905 by Albert Einstein, and it was in a publication called On the Electrodynamics of Moving Bodies. You can find a copy of that in the Principles of Relativity, which is a Dover book. Last time I bought it, which was decades ago, it was $4.95, but still Dover books are the cheapest you can find, and they're normally a good quality paperback binding, so they're really nice to have. Anyways, that one's got that and a bunch of other fundamental papers to relativity, so I definitely recommend everybody have a copy of that, but not try to learn out of it. It's very, very terse and hard to do that. So the special theory of relativity, basically Einstein called it on the electrodynamics of moving bodies, specifically because Maxwell's equations of electricity and magnetism were already consistent with special relativity, and because of that, Einstein was getting weird effects when he considered what would happen if you were to write Einstein or if you were to write Maxwell's equations in a frame where it's moving at a velocity v relative to u. And he found their difference in, for instance, the wave equation and stuff. So ultimately, that's why I called it the electrodynamics of moving bodies, because it was inspired by electrodynamics, but we actually get some very mechanical results. So let me start off by giving you the two principles. The first principle is the laws of physics are the same for all inertial observers. That basically means any frame where it doesn't look like Newton's first law of motion or Galileo's law of inertia is being violated. So if you see objects that are at random, don't have an obvious force acting on them, but at random just start accelerating, then that's a non-inertial reference frame. As you might guess, if you know a little bit about what's to come with general relativity, you might guess, well, when we talk about gravity, we're talking about, for instance, an object just sitting here in the air and all of a sudden it falls and accelerates downward. We don't see an actual force doing that. We call it gravity and say gravity's acting on it. But Einstein's actually leading the way to say that's not an inertial frame because that object doesn't have a force acting on it. Gravity is not going to be a force in the general theory of relativity, but it is acting as if something's accelerating it. So in that sense, it's not an inertial frame. So also in that sense, no gravitational field is an inertial frame. So the first law or the first principle of special relativity is the laws of physics are the same for all inertial observers. In the general theory of relativity, they'll change that by just taking out the word inertial. They'll say the laws of physics are the same for all observers, period. The second principle of special relativity is really the constancy of the speed of light, and that's just telling you that the speed of light is a constant independent of the motion of the source or of the observer. So if I run at you and then run at you at 99% of the speed of light and then turn a flashlight on, you're not going to see this flashlight beam coming to you at 1.99 times the speed of light. You're going to see it coming at you at the speed of light. If I run away from you at 0.99 or 99% of the speed of light, you're not going to see it running at 0.1 of the speed of light or 0.001 the speed of light or anything. You're actually still going to read it as moving at the speed of light. That's really weird. That's not the way things act. We know that if we're on the back of a flatbed truck going at 60 miles per hour, when we throw something forward at 50, we're going to be going a net of 50 plus 60 miles per hour, or 110 miles per hour is what the object we throw will be traveling at. So that's not the case with light. And that's really the two main principles that you need to come up with the results that Einstein did. So the first one we're going to do is we're going to imagine a train car with a very special clock, and it's a clock that uses light to measure time. Obviously, if the two principles are the laws of physics are the same for all inertial observers, which doesn't give you much to jump in, and then part two is the speed of light is a constant independent of the motion of the source of the observer, then you've got to include the speed of light in it somehow. So there's a good way. We'll just make a clock made out of a light beam. So basically, let a light beam do something, and every time it does something, we'll call that 1 unit of time. And the second time it does, it'll be 2 units of time. So let me start by imagining a train car with such a light in it, and I've already got it drawn here. So this is actually a train car as seen by a person sitting in the train. they would say the same train is just sitting there, or a person that's even, you know, strapped to the side looking in. Maybe it's a glass walled train. But the main thing is this frame is moving along with the train if the train's moving at all. So in this frame, the train is not moving. But what we have is a clock, and that clock is going to be one that basically sends a photon of light upwards. It bounces off this mirror and then returns back here, and that'll be a unit of time that we'll call, say, delta t 0. And I'm going to put a subscript 0 on that because that's the time measured by the person that sees the clock being right there with them, both at the beginning of the time interval and at the end of the time interval. So the person right there next to it sees a clock, sees the beam of light leave, sees the beam of light bounce off the mirror, and then sees the beam of light return. That all happened right there by the person, and that person therefore is measuring proper time. Now that proper time, since velocity is equal to distance divided by time, that proper time should be time equals distance divided by velocity. The distance traveled, since I called this d, must be 2d, and the speed of light, of course, is c. So that's the actual time interval. If you took 2 times d and divided it by c, you get the time interval delta t 0, and that's called the proper time. Again, it's proper because the clock that was doing the measuring of the time was at the same place at both the beginning and the end of the time interval. Okay, so that's the reference frame of the train. Now, if we move to the train station's reference frame, as the train happens to be flying by at v, okay, then we get a different scenario. If we're looking at this train, and again, imagine the side is plexiglass, then what we see is a photon leaving here and hitting there, and then bouncing off of there and hitting here, okay? Well, that distance is quite a bit different than the distance that we found in the previous one. And that interval of time, we're going to call it just plain delta t. So in this case, we're going to say delta t is still the distance traveled divided by the time taken, but the distance traveled is this hypotenuse here. And you can see, of course, this distance on the triangle is one of the 90-degree sides. That's d. And then if you consider that the train during this time interval, delta t, has moved a distance L, which might be v times delta t, then you can say, okay, well, I know that this would be half of that distance. So this from here to here would be half of this distance, or half of the L if you wanted to, and this would be a d, so we can just use the Pythagorean theorem. So I'm going to use the Pythagorean theorem on one triangle, but by getting it, I'll multiply it by 2, and that'll give me the total length. So it'll be 2 times the square root of d squared plus L over 2 squared. And then, of course, all that will be divided by the speed of light, because that's how fast, that's how fast the light beam is traveling. Now, if I use L is equal to v delta t, then I'd get delta t is equal to 2 square root d squared plus 1/4 v squared delta t squared. All of that under the square root, and then all of that over c. Now, if I take that equation and let's say solve for c delta t, then I could say c times delta t is equal to, see, all I did was pull the c over to here. So now I'm going to have c delta t, and that'll be equal to 2 times the square root of d squared plus 1/4 v squared delta t squared, like that. Now I'm going to square both sides. So I'll raise this to the 2 power, and I'll raise this to the 2 power, and I'll get c delta t squared is equal to 4 d squared plus 1/4 v squared delta t, again in parentheses squared. So I can continue on, and I would say c squared, which, by the way, this was supposed to be squared there too, c squared now times delta t squared is going to be equal to, I'm going to distribute this 4 through here, and I'm going to get 4d squared plus v squared delta t squared. So that's what happens when I distribute that 4. Now what I'm going to do is solve for delta t, and I'll say that clearly I can get the delta t's over here by doing c squared delta t squared minus v squared delta t squared, and that's equal to 4d squared. So now I can factor out a common delta t squared there, and I get delta t squared times c squared minus v squared is equal to delta t, or excuse me, is equal to 4d squared. Okay, so ignore that. In fact, let me go ahead and make it a little prettier. So this whole thing would just be equal to 4d squared. Now from that, I can finally say that delta t squared is equal to 4d squared over c squared minus v squared. Now I can take the square root of both sides, and I will get delta t is equal to the square root of 4d squared over the square root of c squared minus v squared. And here's where I do some magic. I am going to basically factor out this c squared. Even though it's not in both terms, you can still do it. So let me show you how. Obviously, the square root of 4d squared is just 2d. And then down here, I'm going to say this is the square root of c squared. Well, what do I have to multiply by c squared to get c squared? That's 1. Well, what do I have to multiply by c squared to get negative v squared? Well, that has to be negative v over c squared. So notice if I do actually multiply c squared times v squared over c squared, you see it cancel out, and you just get back that last term. That's how we know we did it okay. All right. Well, I can now make this 2d over the square root of c squared is just c times the square root of 1 minus v over c quantity squared. Well, now I see 2d over c happen to be our delta t0, our proper time. So 2d over c, I can just erase those, and I'll have my final result. That is the time interval measured by us on the side of the track or at the train station is equal to the time interval measured by the person riding the train times 1 over the square root of 1 minus v over c squared. Now, this is often interpreted as delta t0 times gamma, where gamma is defined to be 1 over the square root of 1 minus v over c squared. Getting really lazy on drawing my 2's, so I keep having to repeat them. And another thing that can shorten our writing is that we can say gamma is equal to or defined to be 1 over the square root of 1 minus beta squared, where beta is defined to be v over c. Okay, so these are all things that we can use to make our algebra kind of nice, and in other words, allow us to do complicated calculations without writing so much junk. And our ultimate formula is written in one of two ways. The t is equal to delta t0 over the square root of 1 minus v over c squared, or it's equal to gamma delta t0. That is the equation of time dilation. If you look at this gamma factor, which is this quantity here, v can be at best c, but it's always going to be this quantity be always less than 1. So you take 1 minus something less than 1, and you get something that's less than 1. You take the square root of that, you're going to get something that's less than 1. And 1 divided by something less than 1 is bigger than 1. So one of the rules we need to learn is gamma is greater than or equal to, all right, I should write that the other way. Again, with my stupid writing on the fly, coming up with an idea on the fly is not the best thing when you're making videos, because you almost always do something screwed up. So gamma is always greater than or equal to 1, really is what I should have said. I don't know why I wrote 0. It's greater than or equal to 1. So keep that in mind. That'll help you keep your wits about you. But realizing that that's greater than or equal to 1, that means that this person on the train has a process that takes 10 minutes. Let's say it takes him 10 minutes to listen to a particular song. So let's say it's a Stairway to Heaven or something like that. You know, one of those more long, real rocky songs. So if that's the case, then our person on the train says, oh man, that song took 10 minutes. It was really beautiful, but man, that's a long song. And you say, oh, really? Well, to us, it turned out to be because you happen to be traveling at beta equals root 3 over 2, which is about 0.86603 times the speed of light. It turned out that we actually saw that song lasting 20 minutes. And that is what time dilation is all about. The person that isn't moving measures a time interval delta t0. The person that happens to be the same person that sees the clock with them both at the beginning and the end of the time interval, they would measure that as, say, 10 minutes. But the other people not measuring proper time, they see the clock at one place at the beginning of the interval and an entirely different place at the end of the interval, way over here. So they're not measuring proper time, and therefore they measure a longer period of time, and the longness is the factor gamma. It just happens that the factor gamma is 2 when beta is equal to square root of 3 over 2, or 0.86603. So that's it. I hope that helps you understand the basics of special relativity. We'll talk more and solve a lot more problems later.